Hello, and welcome to another video in this series as we learn the basics of lean in order to write simple maths proofs. Today we're going to continue the theme of contradiction, but combine it with proof by cases. There's a few new ideas also being introduced, so we'll take it slow and steady today. So if you think back to when we were learning about proof by cases, we used a hypothesis and we split that out into all possible cases, and then we looked at each case and showed that all the cases led to the proof objective. In general, that's not true. In general, it can be that some of those cases lead to a contradiction, which means they were never possible in the first place. And that's what we're going to be looking at today. I'll just draw a picture because those words may not make sense if this is the first time you've seen this. So in general, earlier when we looked at proof by cases, we had a hypothesis and we used the hypothesis and established maybe 1, 2, 3, maybe more cases. I don't know, let's say the hypothesis is, n is a natural number, or even let's say an integer. So it might have had 0, less than 0 and more than 0, 3 cases, and we looked at each one and showed that they led to a proof goal. And sometimes that's kind of an easier thing to do, which is why proof by cases is useful. But in those examples that we looked at earlier, all the cases led to the proof goal. But what we're going to look at today is a scenario where you might have cases and some might lead to the proof goal, maybe that one, but others lead to a contradiction. And what that means is they were never possible. So that means you can include certain cases but rule out others, and some proofs require that. So we're going to look at that today. If that sounds a bit abstract, hang in there. We're going to look at quite a simple example to illustrate this. So let's look at a simple task. So here, just to be clear, P is a proposition, so it's not a number like a natural number or an integer. It's a statement that can be true or false, and we've introduced those in previous tutorials. This symbol, if you remember, means negation. It is not the case that. So we're wanting to show that the negation of a statement P implies P. Now you might look at that and say, well, of course, 2 negations cancel out. The not of a not undoes itself. That is true, but what we're going to do is we're going to pretend we don't know that. So we're actually going to prove it in some ways. We're going to say, we're going to prove that not P actually does imply P. So if we can prove this, then we've proved that you can actually cancel out 2 negations. But that's just an interesting aside. The point of this exercise is to illustrate contradiction in a proof by cases. It's not immediately obvious how we'd go around proving this if we don't assume that you can cancel 2 negations. So I'll actually talk through the proof because it's not immediately obvious. It's quite cool when you see it, but it's not immediately obvious. And we're going to use something called the law of the excluded middle. Sounds very fancy. But the idea is very simple. The idea is that a proposition is either true or false. Again, that sounds obvious, but when you're thinking about low-level axioms and definitions, these kinds of very fundamental statements make sense. So at some point we have to agree that a proposition can be true or false, but there's no third option. So just for clarity, although it doesn't matter for today's video, this isn't saying that a statement can't be true and false. That's a different kind of rabbit hole. It's just saying that there's no third option. It's true, false, and nothing else. So from our perspective of cases, the cases could be true, false, but there's no third case. So that's the lens we're going to look at it. So for our statement P, it can only be true or false, and those are the two cases we're going to be looking at. So I could talk through this, but let me draw a picture because it's a lot of words. You can read this in your own time. The slides will be online. There's a blog as well which uses more carefully chosen words, so you can look at that, but sometimes a narration can be helpful as well. So let's state what we're trying to prove. We're trying to prove an implication not P implies P. That's the thing we're trying to prove. And how do you prove an implication? Well, in general, if you're trying to prove A implies B, you assume A and then prove B. That's the general recipe. We assume A is true, and then we can see if we can prove B, assuming A. There are cases actually when there's no need to use A in order to prove B. That's fine. You'll occasionally see that, so I'm mentioning that just in case you come across that on your travels. So for us, we're going to use the law of the excluded middle and consider P, and that tells us P can either be true or false. There are no other cases. So we've got case 1 and case 2, and in this one we've got P is true, and this one we've got P is false. Those are the two kind of scenarios, two cases. And remember, we've got an assumption because we're assuming A to prove B. The assumption here is that is true, that the first part, the antecedent, that's called the consequent, is true. Let's write that here as well. Now using that, can we prove the conclusion? Well, here the other thing that we can assume is that P is true, because that's case 1. Well, that's already the goal, so there's nothing more to do. Job done. We didn't actually need to make use of the other assumption. Actually, that's what we mentioned before. Sometimes you don't use it. So we didn't use A. We were directly able to prove the conclusion, because in case 1 we're assuming P is true. This here, P is true. So that's no more work to be done there. In this one, P is false is the case 2, P is false. So here we have not P is true, because that's the same as P is false. So it is not the case that P is true, P is false. So from here, can we prove the goal, P? If you look at these two hypotheses, these two assumptions, they're of the form not Q and Q. Can you see? If I put a bracket here, bracket there, these two things are contradictory. So every time we have something of the form Q and not Q, doesn't matter what Q is, that's a contradiction. So this is a contradictory case. Case 2, P is false, contradicts the other assumption. So that means the assumption, so this is going back to the previous video, this means that the assumption not P, that has led to a contradiction, therefore this was a false assumption. So this case can't happen. So in summary, only this case is consistent, and as it happens, it leads to the goal. And this case is inconsistent, it's contradictory, so this case can never arise anyway. So this is a way of using a proof by cases by looking at all the possibilities for P to prove this statement. So that's the idea. If that's the first time you've seen anything like that, do kind of rewind or look at the blog to take it in a little bit more slowly. We'll get some practice later anyway when we do the exercise. Just a couple of points in that proof that are worth kind of thinking about. We've already said that two statements of the form Q and not Q are contradictory, and that's how we justified the contradiction not P and not P. We didn't necessarily assume you could cancel those two things out. All we've said is anything in this form, two statements of that form are contradictory, so this contradicts this. That's all we've used. We've not used the idea that these two things can cancel out. The other thing that may feel circular is that in the first case, in this one here, we've assumed P is true to prove P is true. And that looks like a circular argument, but it isn't, because we're actually considering all the possibilities for P. And that means we've looked at the other one, P false, and ruled it out. The important thing there is not that we've ruled it out, but that we considered it. If we didn't look at the other case, then it would be a circular argument. Assuming P is true to prove P is true is circular, unless we say we're looking at all the possibilities for P, including P is true and P is false, and seeing where that goes. Then that's not circular. So let's write something out which is in small steps, and it looks a little bit laborious, but the idea is that these steps are small enough and kind of match what a lean proof would do, or at least the thinking behind it. The lean proof is actually very short, but it's this thinking, this is what's happening under the hood, as it were. So we've got a proof objective. That's always a good habit to start with that. We know that to prove A implies B, we take A as a hypothesis and prove B. So that's what we've done here. We've taken a hypothesis, this assumption, and that's the new goal. So that's how we prove a implication. And then we use the law of the excluded middle to say P is true, or the negation of P is true. P is true or false, and those are the only two cases. So this is the bit where this proof becomes a proof by cases. It's a disjunction. It covers all the possibilities for P. There's no missed gap. So P is true or not P is true. And we look at each of these two cases. So case P is true. You'll sometimes see in mathematical writing that just P on its own means P true. People do it for brevity, I guess. So the case that P is true comes from this disjunction, this law of the excluded middle, and that happens to match our proof goal there. So that case is done. Nothing more to do there. It's trivially true. The other case is more interesting. Case that not P is true. Not P contradicts our assumption that not P is true. So remember, they're in the form Q and not Q, so that's why it's a contradiction. So we rule that out. It means that case can't happen. So only one consistent case leads to P. So that's how you prove that. So the code is not very long, but there's a few new ideas. So I'm going to actually live code it and talk us through that. So you can see here, same standard header as always. We're declaring the variables, and we've got P as a proposition. So it's not a natural number. It's not an integer. It's of type prop, which means it's a proposition, which means it can be true or false. And our proof objective is that the negation of P implies P. So how do we prove A implies B? Well, we assume A and prove B, and the way to do that is to say intro. And what that does when you've got an implication as a goal, it takes the antecedent, the first bit, and makes that into a hypothesis, and then uses that as the goal. So if you look at the state before this intro G, we've got not P implies P as the proof objective, and afterwards we've got not P as an assumption, as a hypothesis. We've called it G, can call it H, and then we've just got P as the new proof goal. So that's how we break down a implication, a goal that's an implication, into an assumption and a new goal. So that's what that does. Just to say, intro is used in different ways. So you'll see it used in other kind of scenarios that aren't an implication, and we'll get to that, or you can have a look, online yourselves. But this is one use of intro. In all those cases, it introduces either a hypothesis or a variable or both. So it can take, a goal and do that. And in this case, if it looks at an implication, A implies B, it turns A into a hypothesis and B into a goal. Right, so how do we proceed? Well, we said we were going to be looking at all the possibilities for P, the cases. So let's do that. So we say by cases, let's call it H, the hypothesis P. What that does, it says, looking at P, we'll do a proof by cases on all the possibilities for P, and in each possibility, in each case, H will be the name of the case hypothesis. So let's see what that has done. It's created two goals. Good. It's even named them case positive, case negative. In the first one, the assumption is that P is true, hypothesis H, and in the second one, it's the opposite. So the assumption here is not P is true. So P is true and P is false. Those are the two cases. And in both of them, you have to prove the goal P. So it's created a proof by cases effectively. And then we use focusing dots because that's a good habit. So that's the first one. And how do we resolve the first one? Well, we've got a hypothesis P, H, which is P, and a goal, which is P. So that's an exact match. So we can just say exact H, job done. You could do as apply H, but when you can do exact, you should. It's kind of a better habit. It's more strict. And the benefit of that is that if you thought that exact should work, but it doesn't, it means there's a bug somewhere or a false logic somewhere, and it's better to uncover that soon, whereas apply can sometimes hide that. Right, the next case is not P. And actually looking at the hypotheses, you can see between H and G, they are of the form Q and not Q, where Q is not P. So we've got a contradiction. So actually, we know from last time that contradiction looks through the hypotheses and finds two contradictory ones and resolves it. So that's done. That is the proof. As simple as that. So yes, there's a lot of thought and concepts that went into that. The proof's not very long. But we had to talk through, how do you prove an implication, and what is the law of the excluded middle, and creating two cases. And the key point today, which was sometimes you'll have cases which support the proof objective, but sometimes you'll have cases like this one, which are contradictory, which means they were never possible in the first place. And that's what we've seen today. So that's a useful kind of proof strategy. And that's kind of a nice thing to see. So that's proven what we intuitively knew to be true, which is the negation of P implies P. It's always useful to use the Infoview. We've done that as we were live coding. So we saw that before intro G, the proof objective was not P implies P. And then afterwards we had the antecedent here set as a assumption, and then a simpler proof objective. So we saw that. And similarly, by cases, HP, we saw two goals being created. They replace the original goal. So it becomes a proof by cases that we've seen before. And we resolved the first one by saying that's exactly the same, and here the two are contradictory, so it rules that one out. So in terms of an easy exercise, we say easy, not to be patronising, but the idea is the maths isn't complicated, so we can focus on the lean ideas. So the challenge here is to prove the other direction. P implies not P. Then you might think that's going to be even more complicated, because we're starting from something simple and we're trying to prove something a lot more complicated, so maybe the proof's going to get ugly. And I guess it could. And what I'll do is I'll just talk through how you might approach that. Is a tip here, actually. But just before I do, it's worth saying that this is the opposite direction of what we've done before. So the two together means it's an equivalence. Let me draw a picture. So before we proved this, and now we're being asked to prove P implies not P. So this is A implies B, and this is B implies A, which we know is equivalent to A if and only if B. So there's an equivalence. So if we can do this, then we'll end up with not P, forwards and backwards P, and that is actually true. So there's an equivalence. Whenever you see this, you can replace it with this, and whenever you see this, you can replace it with this. So that's just a nice little thing to notice. So back to what we were saying about how to prove it. Well, we want to show this, and we could do a law of the excluded middle on P. So we take P true and P false. But actually, let's do something a little bit different. Let's say we apply the law of the excluded middle not to P, but to not P, because you can do that. This still gives us two cases, because we can say this is Q. We can say Q is true, which means not P is true, or Q is false, so not P is true. So let's see where this first case takes us. Not P is, well, it's not that actually, is it? So in order to prove A implies B, we assume A, and we have a goal B. So we assume P here. I should have written that. So assume P, and here we're assuming P as well. And that's a contradiction. So we assume P, and then in this case, not P is true. So that's a contradiction. That means that can't be the case. Let's look at this one. Not P is assumed to be true, and that actually matches the proof goal. So if you're a little bit clever about what you apply the law of the excluded middle to, you can still have a simple proof. Whereas if you did it on P, you might end up with a longer proof. So let's look at that simple proof again. Just there, it's, what is it, through four lines of code. So do have a go at that. I hope you found that interesting. So just to summarize, what we've done today is we used the idea of proof by contradiction, which we learned about last time, and combined it with the idea of proof by cases. And in our example, we saw that some cases, one case, supports the proof objective, but some cases, or another one in our case, it leads to a contradiction, which means we rule out that case. That's the technique that we wanted to look at today. Fantastic. Well, I hope you enjoyed that. Next time we'll be looking at another interesting type of proof called induction. That's really quite powerful. It's a really neat idea, so I'm looking forward to that. See you then. Bye.